All right, guys. Today we're going to pick up rational functions and talk about functions that are polynomials inside of fractions. Is what we're going to be doing today. So the standard of that is r of x is equal to p of x over q of x. So it's like two different polynomials, one on top and one on the bottom. So we've got a lot of stuff that happens with these. We're going to do it kind of, the book separates it into two sections. So I'm going to kind of do section 5.4, and then I'm going to swap over and do section 5.5. But here's the thing: section 5.4 stuff carries over into section 5.5 stuff. So we're going to do all of the section 5.4 stuff, get our hands, dirty with that stuff and get used to that. And then we're going to add in the other things. But the other things are not, I don't think, are that bad. They're things that we've dealt with before. Late check in. Yeah, please. All right. So first thing that we're dealing with, it's a function. So we're going to be dealing with the domain of that function. And to find the domain, since it's a fraction, we're back in chapter 3 when we talked about finding the domain. If there were x's in the denominator, what did we do? Set that denominator equal to 0. So that's nothing new.
Good morning, anxious. Please rise to the pledge of allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Please remain standing for a moment of silence. Thank you. You may be seated. Have a great day.
All right, so set that denominator equal to 0, and then and then solve the equation that creates the method of solving. Even though it may not be the only method for solving that denominator, the method you want to shoot for first is factoring. Okay, try to use factoring to solve instead of other methods. If you can't factor it, then resort to the other methods, because there are going to be questions on quizzes and tests and final exam that ask you just to find the domain. If all you have to do is find the domain, then yeah, you can use the other methods. But if you're going to do everything else that goes along with that rational function, then factoring is going to help you out in doing some of the other stuff. So try to use factoring when you're solving that denominator set equal to 0 to get the domain of that function. All right. So, and then after we found the domain, notice I said after we found the domain, then try to simplify the fraction. And we're going to factor and cancel to do that. So we'll see this when we get to the examples. Factoring and canceling the matching factors. I guess we should write that too, matching factors. So if we're going to have to factor anyway to simplify the fraction, that's why I say when you go do the domain, do it by factoring, because that just gets you one step ahead when you go to simplify. All right, it's not necessarily just because I want you to be good at factoring, which I do, but it's going to help you when you do the next thing. And once you've simplified, then that creates some of the things that we'll talk about in section 5, and it also makes the next thing a little easier. Okay, so the simplified version is where we get our asymptotes. All right, so asymptotes are the imaginary boundary lines that shape a graph. Okay, so imaginary boundary lines that shape a graph. That's what an asymptote is. And there are really 3 different kinds that we got to watch out for with this. And we'll start with probably the easier one, which is vertical asymptotes. vertical asymptotes, once you've factored the denominator and got the domain, a lot of times your vertical asymptotes are going to be matching with the numbers that x cannot be. But you won't always have everything that's in the domain that's listed there. You've got to look at the simplified version of that. So vertical asymptotes, we're going to set the denominator of the simplified version So it's a lot like finding the domain, but it's the simplified version that we're going to use for vertical asymptotes out of that. So once you've simplified, set what's left in the denominator equal to 0, solve those equations. Those equations are going to be your vertical asymptotes. So they're going to look like x equals some sort of some number. Is what your vertical asymptotes are going to be. They're going to be equations. X equals something in there when we do those. Okay, not going to be just a number. It's going to be an equation because we're vertical lines are what they are. So that's where the x equals comes from. Vertical lines. All right. So it's opposite of vertical. Horizontal. Horizontal asymptotes. I'd say number 2 on the list of easy when it comes to the asymptotes that we've got to deal with. Horizontal asymptotes occur with 2 different rules. And I'm a rule person on this. If you'll memorize these rules, it's much easier than doing long division every single time. You could do long division with every single polynomial fraction and get this information. I don't think that's a good method. I think just remembering these rules is the best way to do that. So the first occurrence of a horizontal asymptote is if the degree of the numerator is less than the degree of the denominator. Then the horizontal asymptote and we'll abbreviate that HA from here on out just so we don't have to write that over and over, is y equals 0 automatically. No calculation required. Okay. An example of a problem that has that might be something like this: x squared plus 9x minus 3 over x cubed plus 1. I use that example because it won't factor, the top won't factor and the bottom will factor, but not much, not enough to work here. But the degree of the numerator for this example is what? 2. The highest exponent is 2. The degree of the denominator is 3. 2 is less than 3. It doesn't matter by how much it's less than, as long as the top is less than the bottom. Okay? If it were x squared on top and x to the 16th on the bottom, still got a horizontal asymptote at y equals 0. Okay? As long as the top is smaller than the bottom in degree, then you have a horizontal asymptote at y equals 0. The great news about this is that it doesn't matter if you use the simplified version or the original version, the rule still stands. It's a rule. It means it's always that way. It never changes, even in the simplified version. So whether you look at the original or the simplified, you can get the horizontal asymptote by looking at that. Okay, degree of the top less than degree of the bottom. It's y equals 0, automatic. Memorize that rule. That's important. You've got to know that. Okay. All right. Good news is there's only one other way that a horizontal asymptote exists, and deals with the degrees as well. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote, I'm going to abbreviate HA, is at y equals A over B. That is the ratio of the leading coefficients. An example of that, 3x squared plus 5x minus 7 over 4x squared minus 2x plus 13. Again, I picked that example advantageously so that it won't factor and it wouldn't simplify. So I don't have to worry about that stuff. And I look at the leading coefficients. What's the leading coefficient of the numerator? 3. It's the number that's in front of the highest powered term. Okay, so the highest powered term is x squared. So it's a 3 in front of that. Highest powered term in the bottom is x squared. There's a 4 in front of that. So the horizontal asymptote, because they're equal, is going to be at y equals HA at y equals 3 over 4. Okay. Those are the only two ways that a horizontal asymptote exists. Okay. No other way that you could have a horizontal asymptote. Okay. So we got vertical asymptotes. Those are going to exist pretty much on every problem. Unless the denominator completely cancels out when you simplify, you're going to have vertical asymptotes. Horizontal asymptotes only happen if the degree of the top is smaller than the bottom, and it's y equals 0. If the degrees are the same on top and bottom, x cubed over x cubed, x squared over x squared, x to the 75th over x to the 75th, that sort of thing. Those are the only ways that horizontal asymptotes exist. Okay, that means you won't always have horizontal asymptotes. Okay, there are going to be occurrences where there are none on horizontal asymptotes. The other type of asymptote that we have is what's called an oblique asymptote. An oblique asymptote, if you Google this, you might find some folks call them slant asymptotes. It's the same thing. So if you Google or look for videos to help you with this or something like that, slant asymptotes and oblique asymptotes are the same thing. Well, slant kind of helps me understand what this looks like. We know vertical asymptote means straight up and down. Horizontal means flat. Oblique really doesn't mean much, right? But slant means a lot. Slant means it's going to be a diagonal line. Asymptotes are always going to be these straight lines for us with rational functions. So slant asymptotes, oblique asymptotes, same thing. And they have a rule for when they exist. They don't always exist. But when they do, it has to follow these rules. If the degree of the numerator is 1 more than the degree of the denominator. Y'all hear that? There's it. All right. Then the oblique asymptote. So oblique asymptotes. Only going to happen if the degree of the top is one more than the bottom. This is the only time it happens. Oblique asymptote, and we'll abbreviate that from here on out to as OA, is the equation y equals mx plus b obtained by long division. Everybody loves long division. Of the polynomials. All right. Long division is the only way that we're going to create that. That mx, y equals mx plus b, that is the quotient when we do the long division. Okay? So this, whoops, highlighter. This is the quotient when we do long division. Okay? An example of a problem that would have an oblique asymptote might be something like this. F of x equals x cubed plus 27 over x squared plus 9. I know that the numerator would factor a little bit, but the denominator will not factor. So there's nothing that would simplify here, even if I tried. But the numerator has a degree of 3. The denominator has a degree of 2. That's one more than the bottom. That's the only way that an oblique asymptote would occur. And then we would do long division to find that thing, okay, or that oblique asymptote, that equation for that. Okay, so vertical asymptotes, almost always going to have those. Denominator, after you simplify, set equal to 0. Horizontal asymptotes, what's the rule for horizontal asymptotes? Numerator's less than denominator. What's the horizontal asymptote? Y equals 0. That's the easiest. That's probably maybe the easiest one because it's y equals. You don't have to do any kind of calculation. And then what if the degrees are equal? Yeah, the leading coefficient ratio. That's what it's going to be. Simplify that fraction if it will. So those are the only ways that horizontal asymptotes occur. The only way that oblique asymptotes occur is if the degree of the numerator is what to the degree of the denominator? One more than. Numerator is one more than the denominator. So that's cubed over squared, fourth over third, fifth over fourth, something like that. Okay, that's got to be those things. And you're going to use long division to get there. So with that, those rules occurring and these certain ways the degree has to be done or has to work out for those to exist, what do we know about horizontal asymptotes and oblique asymptotes? Can they happen at the same time? No way. If the rules for the degree are different for each scenario, then there's no way that horizontal and oblique asymptotes occur together. So if you're working a problem, we're going to look at them. We're going to find the domain. We're going to find all those asymptotes. If we found that it had horizontal asymptotes, we automatically know that it's none on oblique asymptotes. All right. If it's none on horizontal, does that automatically mean that they're obliques? No, it's possible that we don't have oblique or horizontal. So horizontal and oblique asymptotes do not have to exist. Okay. a good portion of the ones that you're going to see in practice and in examples are going to have those because that's what we're studying, but they don't have to be there. Okay, it's possible for it to just have vertical asymptotes. It's possible for it to not have, if the fraction were to simplify in a nice way, where there was 1 on the denominator, that it ends up looking a lot like something that's not even rational. That's just a regular equation. So let's start with an example, and we're gonna find the domain and then these asymptotes. And we'll add in the other stuff in just a little bit. Okay, so first example, f of x is equal to x squared plus 7x plus 12 over 4x squared minus 1. So we're going to find the domain and any asymptotes. So we're going to find the domain first. How do we find the domain? Okay, denominator equal to 0, so 4x squared minus 1 equals 0. And then what method are we going to try to use to solve that? Factoring is what we need to try to use here because we're going to simplify that fraction, or try to, in just a little bit. So let's try to use factoring. How do we factor 4x squared minus 1? Difference of squares. Good job. So that means it'd be 2x plus 1, 2x minus 1. Set those equal to 0. You guys ought to be well versed in this by now. Negative 1/2, positive 1/2. So our domain x cannot be plus or minus 1/2. And we'll just write it in set notation for today. Now, what we're going to do is we're going to use that factored form of the denominator over here. And we're going to factor the numerator as well, if we can. So how do we factor x squared plus 7x plus 12? X method, got to multiply to be 12 and add to be 7. 3 and 4, so that's x plus 3, x plus 4. All right, we did all that work. Will anything cancel out? No. Okay, that's okay. The factored form of that can be helpful when we do some other things out of that, even though it did not simplify the fraction any. Getting that factored form can be really helpful when we start doing some of those things from section 5 as well. Okay, so don't think you've wasted that. We're going to use it in a little while anyway. All right, so let's first find the vertical asymptotes, VA. And we got the factored form and nothing canceled out. So our vertical asymptotes are going to come from where? Denominator set equal to 0, which ends up being the exact same equations that I found down here when I found the domain. Okay, so I've already done all that work, right? I don't have to do it again. That's the beautiful part of this. If something had canceled out, and we'll get to some that do, then you're going to have less vertical asymptotes than you do pieces in the domain. This time we have the same ones. Okay, so x equals 1/2, x equals negative 1/2. Those are the equations of the vertical asymptotes for this particular rational function. Okay. We'll look at the graph of it later. All right, oblique asymptotes, or excuse me, let's do horizontal, then oblique. Horizontal asymptotes. Since it didn't simplify, I'm going to go back to the original and look at the degrees. They're the same, right? X squared and x squared. So that means my horizontal asymptote is going to be where? The ratio of the leading coefficients. 1/4. What's that mean about the oblique asymptotes? All right. My brother would say there ain't any. I'd say that too. All right. Or there ain't none. Is the funnier way to say that. So there are no oblique asymptotes out of that. Okay. Not too bad. First section here doesn't get too bad. This is what we're doing. Okay. Let's look at example 2. We can make something else happen here. X squared plus 7x plus 10 over x cubed minus 25x. Again, we're going to do the same things. We're going to find the domain, the vertical asymptotes, horizontal asymptotes, and oblique asymptotes if they exist on the horizontal or obliques. Okay? Just find that domain. What do I do? Factor the bottom. So set x cubed minus 25x equal to 0 and factor that. How do I factor that? GCF of an x, that leaves x squared minus 25. Yeah, so that gives you x plus 5 and x minus 5. So we get 3 numbers that get left out of our domain. Get x equals 0, x equals negative 5, and x equals positive 5. And I'm fine with you writing it just like that. 0 and plus or minus 5. That's what x cannot equal. The interval notation for that would be this long, because you got to go from negative infinity to negative 5 to 0, 0 to 5, and then 5 to infinity. So it'd be 5 pieces. All right. Now, after I've done that, I'm going to use that factored form that I've got right there in simplifying this fraction. X plus 5, x minus 5. And then let's factor the numerator. X plus 2, x plus 5. And again, that comes from x method, multiply to be 10, add to be 7 out of that. Now what happens? The plus 5s cancel out. So the simplified version has x plus 2 over x minus 5. So there we have the simplified version there on the right in purple there. X plus 2 over x times x minus 5. I'm not multiplying that back out. I don't see a need in doing that. So just leave it in that factored form. That's the way that we will generally leave things. So now let's look at vertical asymptotes, because this is where when things cancel out, vertical asymptotes change from what the domain was, right? So which one of these 3 things here did we lose when the x plus 5s canceled out? The x equals negative 5. So our vertical asymptotes are the other 2. X equals 0 and x equals 5. Comes from just setting those 2 equal to 0. So if it's confusing to go back and look at which one dropped off, just set the denominator equal to 0 and solve it again. It's the same thing. Okay. So x equals 0 is a vertical asymptote, and x equals positive 5. So 2 vertical asymptotes on this one. Notice we had 3 pieces, 3 numbers that were dropped out in the domain, but we only had 2 vertical asymptotes. That's because it's simplified. When we get into section 5, we'll talk about what happened to that x plus 5. What did that create in the graph? And then horizontal asymptotes. So let's go through our horizontal or obliques, because these are the rules about degrees. So we can either look at the simplified version or the original version to follow those rules. What's the degree of the original version on the top? 2, and on the bottom it's 3. Okay, so the top is smaller than the bottom, so what should we have? Y equals 0 as a horizontal asymptote. Look at the simplified version. What's the degree of the top? What's the degree of the bottom? 2. Still the same rule. The top is smaller than the bottom. So it doesn't matter which one you go to. I usually go back to the original just because I can glance that. I don't have to multiply anything back out in my head or anything. So that works out fine. So horizontal asymptote at y equals 0. So what's that mean about the obliques? Ain't none. All right. Questions so far? Most everybody should have seen at least a good portion of this in Algebra 2. May not have seen much of it, depending on if you had it last semester. Yeah, sorry, your teacher stunk last semester. I'm referring to myself. We missed 20 days of school. All right, let's look at the third one here. Excuse me. X cubed plus 8 over x squared plus 6x plus 8. That's our rational function. And we're going to do the same things. We're going to find the domain. We're going to find the vertical asymptotes. We're going to find the horizontal asymptotes. And obliques, if those exist. We don't know if they do yet. So where do we start? Factoring the denominators. So setting x squared plus 6x plus 8 equal to 0 and solving that. Factoring is the method that we want to use to do this because we can use that to simplify later on. If you get stuck and you can't factor it or you just can't find the numbers, don't leave the domain blank. Use quadratic formula to solve that. Do something, okay? You can get answers for parts of these things without, getting everything. So that'd be x plus 4 and x plus 2, right? So x plus 4 equals 0, be x equals -4, and x equals -2. Those are our two numbers that are left out of the domain. -4, -2. I'm going to go to the simplifying stuff. So x plus 4, x plus 2. And then will the numerator factor? An important thing there. Because it won't simplify if it won't factor. Ooh, it's a sum of cubes. And everybody remembers how to factor sums of cubes, right? Some you don't do a lot, right? We don't factor sums of cubes very often. So we got to remember that little format. You got a long factor and a short factor. What's the short factor? Yeah, it's the same as the pieces that are cubed. Plus on the inside because that's a sum of cubes. Okay. Well, if you use one of the x's, that means x squared is left. If you use one of the 2's, that means 2 squared is left, which is 4. And then in the middle, opposite of the product, yeah. If you don't remember factoring sums and differences of cubes, they come up every now and then. Not terribly often, but enough that you got to make sure you know how to do it. Okay, now what happens to our factors here? That x plus 2 cancels out. Okay, so simplified version. Now, what's that mean about our vertical asymptotes? How many we're going to have? 1, because how many factors are left in the denominator? 1, that x plus 4. So the vertical asymptote would be x equals -4. Okay. Now, go to the degrees of the numerator and the denominator to decide about horizontals and obliques. What does this one have, or does it have either of those? Yeah, whether we look at the original version or the simplified version, the degree of the top is 1 more than the bottom. So what's that mean about horizontal asymptotes? Ain't none. Means we got an oblique. Okay, so we've got to solve and do some long division to do that oblique asymptote. And you get a choice whether to do the original version or the simplified version when you do the long division. The only thing that can come into play is with some of them, you may have to multiply it back out on the simplified version. If you got more than one factor on top and bottom, top, or more than one factor on the bottom, you got to multiply it back out to do that long division. We're lucky on this one that the simplified version doesn't have extra factors in it. So we could just do straight long division with the simplified version or do it with the original version. I tend to always just go back to the original. That way, if I screwed up something on the factoring, at least I'll get the oblique asymptote right. But that's up to you what you want to do there. We'll do it both ways. I'll show you both ways. All right, so if I go to the original, there's advantages to both, so I want to show you both ways. I'm dividing, my divisor is the denominator, x squared plus 6x plus 8. The numerator is the dividend, that's what I'm dividing into. So I got x cubed plus 0x squared plus 0x plus 8. Y'all guys remember doing that? Having to put the zeros in there? That's an important thing. If you don't put them there, it's going to get messy. Okay? And then we look at the first term. What times x squared gets me x cubed? X. Then distribute x cubed plus 6x squared plus 8x. Parentheses, subtract. X cubes go away. We get a negative 6x squared and a negative 8x, and we bring down the plus 8. Now, what times x squared gets me negative 6x squared? Negative 6. Subtract. Let's go away. It ends up being positive 36. Should be 28. And it ends up being positive 48, and 8 would be 56. Now, does this 28x plus 56 even matter? Why or why not? My oblique asymptote is x minus 6. Y equals x minus 6. Because it's the quotient of that part. So when you do the long division, the quotient is going to be that. The 28x plus 56 is called the what? The remainder. Doesn't really matter what the remainder is. Okay? It shouldn't take you more than 2 steps in your long division. If it's taking you more than 2 steps, something's wrong with what you're doing. Okay. Now, so that's doing the original version. Let's do the long division with the simplified version. X plus 4 into x squared minus 2x plus 4. Again, we're looking at the front term. X times what gives me x squared? X. That should not be a surprise. Distribute x squared plus 4x. Subtract. X squareds go away. That's negative 6x. Bring down the plus 4. What times x gets me negative 6x? Negative 6. That should also not be a surprise. Parentheses, subtract. And then we get a remainder of 28. Again, same quotient, just done from a smaller problem. Doesn't matter which one you do, just keep in mind that if your simplified version has more than one factor on either top or bottom still, then you've got to multiply that back together before you do your long division. All right. Either way, you still get the same thing. And it should always be y equals mx plus b form for an oblique asymptote. Always. Okay?
So I have a question now.
Yeah.
On the long division, like if it was just real instead of on the remainder, would you have to go in and simplify all that?
Yeah, if you were doing the remainder, you'd write plus 28 over x plus 4. Or plus 28x plus 56 over that. All right. So that's basically the things in 5.4 that it asks you to do. So let's add in a few things in 5.5. So 5.5 adds in, we've already been doing domain. So we're just going to go to the next example. We're going to find the domain, the asymptotes, what are some other important things that we found with functions? Every type of function we've dealt with. Say it again. Range, yeah, we could talk about that. What's something that we could algebraically find? Intercepts, that's an important thing. Intercepts. And then we're going to find what's called holes and crossing of asymptotes. The crossing only occurs with horizontals or obliques. We don't have to worry about it crossing verticals. Okay. I wanted to show you the graph before we get too deep into this of like number 3, example 3 there. So with your graphing calculator, I'll show you the graph. You can kind of see all that stuff happening. And the graph's going to be helpful when we're trying to do all these intercepts and all that stuff too, that we can check things with that graph and make sure it's happening. All right, so example 3 is the one that we're going to graph first. So I'm just going to type in the original version. I'm not worried about simplifying and all that stuff. I'm just going to graph the original because the graph of this original one is exactly the same picture as the graph of the simplified one. Okay, that's another way to check and make sure you simplified it the right way. Okay, so numerator, parentheses, x to the third plus 8, close the parentheses, divided by parentheses, x squared plus 6x plus 8. Okay, so I'm putting the numerator in parentheses, the denominator in parentheses. That is a important thing. Now, look at our graph. We can see right here, this is kind of turning up, almost getting vertical right there. If we zoomed out, we'd see it getting more and more straight up and down. That's where our vertical asymptote was. Where was our vertical asymptote? -4. So on the graph, -4 is right here, right? And so right there, we can see as this line is kind of veering toward it, but when it gets closer and closer to that vertical line, it's going to get, more and more vertical, right? We had an oblique asymptote for that one. And can we see how this is slanted right here? What was the equation of our oblique? X minus 6. So that's a slope of 1 with a y-intercept of -6, right? 1, 2, 3, 4, 5, 6. Slope of 1, so that should intersect it. Looks about like that, right? And we see that line's kind of shaped by that. If we could actually even graph that oblique asymptote if we wanted to on y2, so x minus 6, hit graph, we can see that's shaping that graph out of that. So you can tell when there's an oblique asymptote, when there's a vertical asymptote by the graph of your polynomial function. All right. So we're going to kind of use that graphing idea to help us a little bit when we do these next few examples and check some things with that. All right, so examples 4, 5, and 6, we're going to do a little bit more stuff, okay? So we're going to find domain, asymptotes. We're going to find the intercepts. We're going to find whether there are holes in the graphs, and then whether or not the graph crosses an asymptote out of that. So let's just dive in. X squared minus 4 over x squared plus 5x minus 14. We're going to find the domain, vertical asymptotes, horizontal asymptotes, oblique asymptotes, and I'll go over here and do holes, intercepts. And we'll get the crossing later. All right, so let's start with the domain. How do we do that? Factor the denominator, x squared plus 5x minus 14. What are my factors? Yeah. So that'd be x equals 2, x equals -7. So our domain, x does not equal -7 or 2. And again, I'm just using that factored form in the denominator. And then I'm going to factor the numerator to simplify this fraction if possible. So what's the numerator factor as? Yeah, it's a difference of squares. So x minus 2's cancel out. So the factor or the simplified form is x plus 2 over x plus 7. It's fairly tame, not a whole lot fancy about that, but it is a rational function. What's its vertical asymptote? X equals -7. Again, you can get that from the domain stuff. What didn't cancel out was the x plus 7, so that's going to give us that. Or you can just go to the simplified version and set the denominator equal to 0. Same answer. Okay, so we should, if we graph this, we should be able to imagine an x equals -7 vertical asymptote shaping the graph. All right, now here's where the holes comes in. Holes happen when a factor cancels out. Okay, there is a hole at the x value of 2. Okay, it's a hole in the graph. We need to find the y value that goes with that. So all we got to do is plug that into the equations. Okay, so we're going to find f of 2. I'm going to go to the simplified version because it's shorter, right? So 2 plus 2 over 2 plus 7 be 4 over 9. So there's a hole at 2, 4 over 9 on the graph. Now remember some of the pictures in the past sections where they'd have the graph, they'd have an empty circle kind of in the middle of the line. That's what this is. Okay? It's an empty circle right in the middle of the line. Okay? So that's an empty point on that. Holes only occur if you get a factor that cancels out. That's the only time they happen. They don't always happen, but that's the only time they do. Okay? Now, let's look at our degrees and get our horizontal and oblique asymptotes. Okay, degrees are equal on the simplified version or the original version. So what's our asymptote? Y equals 1. Yeah, 1 over 1, which would just be 1, right? And that means there are no obliques. We've found domain, asymptotes. We found the hole in the graph. Now we need to find the intercepts for that graph. What kind of intercepts can we have? X-intercepts and Y-intercepts. How do you find X-intercepts? It's at what equal to 0? The whole thing. It's the same thing as making Y 0. So I'm going to set the simplified version equal to 0 because it's smaller, right? How do you solve that? Yeah, and then cross multiply, yeah. So it's just going to end up with the numerator equal to 0. So to find x-intercepts, we're going to set what equal to 0? technically the numerators, what you're always going to end up with is the numerator set equal to 0. And then, so x equals -2. So we got an x-intercept at -2, 0. How do we find y-intercepts? Yeah, we just do function value for 0. That's 0 plus 2 over 0 plus 7, 2/7. So y-intercept at 0, 2/7. Now, the last thing on the list of things to do was decide, does this graph cross the horizontal or oblique asymptote? Well, we only have a horizontal asymptote, right? So the way to decide if it crosses it is to set the equation. So this is the part about does it cross the horizontal asymptote. We're going to set the equation x plus 2 over x plus 7 equal to the horizontal asymptote. The y value of horizontal asymptote is either going to be 0 or that ratio of the leading coefficients. Here we're setting it equal to 1, and we're going to solve that equation. How do you solve that equation? Put it over 1 and cross multiply. X plus 2 equals x plus 7. And then what happens here? Yeah, if you try to simplify or get like terms together, you end up with 2 equals 7. Is that true or false? False. That means there's no solution. If there's no solution, that means it doesn't cross. Okay. Not too bad there. Let's look at the graph of this one just to verify some of this stuff. I'm going to graph the simplified version because I'm quicker to type it in. Parentheses around the top, division symbol, parentheses around the bottom. Hit graph. -7 was our vertical asymptote, right? Right here. See how that's shaping the graph? Our horizontal asymptote was at 1, right here. See how that's shaping the graph? That looks good, right? Where's it crossing the x-axis at? They're at -2, right? So if I type in, if I hit trace -2, look at the y value down here, it's 0. It's the right x-intercept, right? What about that hole in the graph? What's going to happen if I type in, what was the x value for the hole? 2. So I'm going to hit trace the number 2. 0.4, is it 4/9? 4 over 9 the same as 0.4 repeating? Yes, that's the right value. There is a hole in the graph there. Okay. The graphing calculator can't handle that too well. And if let's look at the difference in the original had x squared. Oops, x squared. Let's try again. There we go. -4. Close parentheses divided by x squared plus 5x minus 14. I'm going to graph that one. And it should lay right on top of that, right? That we know we've simplified it the right way because that happened. Now, if I hit trace and that +2, now notice, because I got the color version here, you guys, a lot of you have that. It's in blue down here. That means that's talking about the Y1 that I put in. I'm going to press the up arrow and hit trace 2. Hang on. Trace Y2. Now, on the unsimplified version, I put in a 2. Notice what the y value is. Blank, because it's the whole. The simplified version, you can get the value of the y value where the whole is, but you won't. It will think, oh, there's the point there because there's nothing to cancel out with the simplified version. With the original version, it's going to say, oh, there was a cancellation that happened there, and there's not a y value that goes with that number. So that's where that hole exists at. Okay, so the hole is a little bit confusing if you graph the simplified version, because you would think, hey, if it's a hole there, then I shouldn't get an ordered pair. Well, yeah, but your calculator it doesn't really understand where you got your simplified version from. Yeah. I got it. I just hit it so you could see those ordered pairs there because it covers it up. All right, let's do another. This is number 5. F of x is equal to 6x squared plus 9x over 3x minus 2. Again, we're going to do all of those things or find the domain. This is the last one in. Go back. Domain, vertical asymptote, horizontal asymptote, oblique asymptote. Get holes, intercepts. All right, let's get the domain. Should be easy on this one. Not much going on there in the denominator. Set it equal to 0. Positive 2/3, right? X is not equal to 2/3. Fun. All right. I didn't even have to factor anything. But I need to factor the numerator to see if something might cancel out. GCF would be 3x. That'd leave us 2x plus 3. Does anything simplify? No. Somewhat good news, I guess. I don't know. What's the vertical asymptote then? X equals 2/3. Nothing canceled, then the asymptote is the same as the domain. Okay. Horizontal and obliques, we'll get that first. Since nothing canceled, what does that mean about the holes in the graph? There ain't none, right? There aren't any. No cancellation, no holes in the graph. Okay. Now, degrees, horizontal and obliques. Since nothing canceled, I'm going to go back to the original. Degree of the numerator in the original is 1 more than the degree of the denominator. So that means horizontal asymptotes no existo. And obliques do. Oh. Long division. Nobody likes long division. Why they even admit that? So 6x squared plus 9x plus 0. Again, I'm just putting that 0 in there as a placeholder so I kind of can line things up. What times 3x to give me 6x squared? 2x. 6x squared minus 4x. Subtract. X squareds go away. 9 minus -4 would be 13. Uh-oh. I'll do a little thinking here. What times 3 gets me 13? It's okay. It's a fraction. So the last step of this. What times 3? Over 3. Just doing a little simpler problem over there. Get that to happen. So when I multiply that out, that gives me the 13x. It doesn't matter what -2 times 13 over 3 is. It's -26 over 3. But it really doesn't matter because we know what's left is the remainder. We've got what we want up here in the quotient. That's the only thing we want. Oblique asymptote, y equals 2x plus 13 over 3. Next thing to do, intercepts. We're going to find x-intercepts, y-intercepts, and then we'll have to do the does it cross. Fun stuff. So, how do we find x-intercepts? Set the whole thing equals 0, but we end up, the shortcut is that we can just set the numerator equal to 0. Does the same thing because it's always going to cancel out the denominator. So the numerator is 6x squared plus 9x equals 0. So we factor that, 3x, 2x plus 3, 3x equals 0, 2x plus 3 equals 0, x equals 0, x equals -3 over 2. We have two x-intercepts here, 0, 0, and -3 over 2, 0. What do we know what's special about 0, 0? It's also a y-intercept, yeah, because it's the only place that the x and y intercepts are exactly the same. So go ahead and list that there. If I want to be, show that work or something, or if I encountered a problem that only asked me for a y-intercept, that could happen. Then this is how I would do it. Plug a 0 in for x. That gets us 0 over -2, which is 0. So that's also where that comes from. Okay. So we have our x-intercepts, 0, 0, and -3 over 2, 0. That 0, 0 also ends up being a y-intercept. So we found our intercepts. Last thing to do is decide whether that crosses the asymptote, the horizontal or oblique. We have an oblique asymptote this time. So we're going to set the problem, 6x squared plus 9x over 3x minus 2 equal to that equation of the asymptote, which our asymptote was at 2x plus 13 over 3. Yeah, how do we solve that? Put it over 1 and cross multiply. So I'm multiplying by 3x minus 2 on both sides. So 6x squared plus 9x. And then I'm going to multiply that out. Good old distributive property. 6x squared again minus 4x plus 13x minus 26 over 3. What's going to happen here? Which means no solution, right? Because it's false. Does not cross y equals 2x plus 13 over 3. If it did cross, you'd get x equals something. And that would tell you the x value where it crosses at. And you could plug that into the function and get the y value where it crosses. If it crosses, you're going to get an answer. These we're not getting answers for, okay? All right, practice problems for these two sections, page 373, 13 through 54, page 382, 7 through 38. Pay attention to the instructions. Don't end up doing extra work on these. Pay attention to what it's asking for. Be able to think your way into just doing what it asks for. Don't get into the habit of, I've got to do all of it or I can't do any of it. Know it well enough that you could do an individual part. out of that. Because on the quiz, I'm not going to ask every problem that you do everything on. And you'll run out of time if you do it that way, okay? So working on those,